Welcome to the course Introduction to Algorithm. My name is Sourav Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. So today is the fifth lecture, lecture number 5. And in this lecture we will cover heap sort. So we will start with the data structure heap. What do you mean by heap? Then we will discuss the max heap, and then we will slowly move to the how we can use the max heap to have a sorting algorithm. So that is the heap sort. So that we will discuss in this lecture. So just to recap what we did in the last lecture, lecture 4, we discussed quick sort and the version of the quick sort, randomized quick sort we discussed in the previous lecture. So let us start with this lecture, which is lecture number 5. I welcome you to this lecture on heap sort. So this is basically start with the data structure heap. So heap is a data structure which we need for some problem which is called priority queue problem. So let us just start with what do you mean by priority queue problem. So priority queue, what we have a dynamic set S of some elements, and this element say S is this at some point of S is the S set is dynamic. Dynamic means at any point of time anybody can join from in this set and anybody can delete it. So this insert operation is make this set dynamic. And who are the elements? Elements are basically key value of the element. So basically this can be related to a database problem. In a database problem we have each data has some attributes, say for example student record. So if you consider student record, it has some field or attributes. So each it has some field or attributes. So student roll number, student name, student CGPA, student age, student address. So this is a element. So this is pointing to this record. So this is one record. So among these attributes or among this field, we consider one field as a key field, and we will do all the operation based on the key field. We will search a record based on the key field. So that key field is one of this field we choose as a key field depending on our applications. For student record, we can choose this key field to be say CGPA. So in that case, if we want to get the student in our database whose CGPA is maximum, so we should able to do that operations. So basically we have some records. If you relate this to a database problem, and each record is associated with some value. So this is a this field is a key field or key of X. Key of X. Key of X. So this is our key field, and this this is let me erase this. So yeah, so this is our basically key of X. So among this one field is we consider to be key. So these are the basically keys, and each is associated with a different record. Okay, so different record we have. Basically we have few records we can say. So this is corresponding to x1, this is corresponding to x2, x3, so pointer is there, but these are basically key field of those particular records. So basically we have some numbers, say n numbers at some point of time, and we want to do some operation on this number, and this set is dynamic. This set is dynamic, that means we have we should able to do the dynamic operation like addition. We should insert means the addition. So we should able to perform that. So now how to do that? So we are looking for a data structure for this S, for this dynamic set S, so that we can perform few operations like we should able to insert a record. So suppose this is the current position of S. Now suppose we want to insert say 4. So how we can insert? So which data structure we follow? I mean, so whether we can have an array for this. If we just think of an array of this, array for this, so we can maintain this in an array say, then we put all these numbers over here, all this key values over here, this is 10, this is 15, 9 and so on, and we can keep some of the field to be empty over here. So, whenever a new record will come, we can just insert here. So, suppose we are inserting 4. So, that will cost us a linear time maybe, because if we have to search the empty one, otherwise we can have a index where is the we are ending, then we can have a we can just insert at the next. So, that is a array implementation. And also to find the maximum, basically we want to find the largest element, largest key value of this S. So, the largest key value is here 11. So, if this is the situation, if 4 is inserted, we can add 4 over here. So, at this point largest is 11. So, we want to perform a operation that is called max operation, max of S, that should able to return us the largest element, largest key value, largest record whose key value is 11. So, that means that should able to return the record whose key value is 11. So, 11 should be, so that we want to that operation we want to do. So, if you keep in array, what we need to do to find the maximum, we need to search this array, because this is just an unordered array. If you put it in an unordered array, we need to search in this array. So, if there are n elements, so searching will take linear time. Okay. Now, if you sort it, then if you do the binary search, that is log n time, but again sorting will cost us n log n time. So, that thing we need to take care. So, but if it is just an unordered array, it will take a linear time. But we need to do something in better way. So, we need to think of a data structure for doing this. Also, one more operation we need to think, extract the maximum. That means we want to find the maximum, that is 11. If this is the current situation on this example, and then we want to delete this from this database. We want to delete this from this set S. So, that is called extract max, and then we want to have a increase key value. So, suppose this is a key value of some record. Now, this got changed. Suppose a student got more number in the next semester. So, this 9 will be say some more value. So, we have to go and change this. So, this is called increase key value of a record or of an element. So, basically here S is a set of elements which is dynamic, and each element is associated, I mean these are basically key values, and these maybe you can think coming from some record database problem. But for the simplicity, just think about S is some numbers, S is n numbers are given, and we want to perform, these are the operation we want to perform. So, max S we have discussed, we want to return the, we want to get the maximum element, maximum largest key value. So, maximum key value in this set S, and then the extract max. So, after getting the max, we want to delete it from this S. So, that is the extract operation, extract max. So, these are the operation we should able to do. And another operation is we have discussed, that increase key. We want to take a record whose is having a key value, we want to change that key value to new key value k. So, we can go there, we need to go there and change it. So, if it is an array, just we need to search the record. So, that is linear time, then we can change it. But we want to do it much more faster way to do all these operations. Okay. So, that is our goal. So, we want to have a data structure implementation on this set S, this dynamic set S. So, that is the problem. So, problem is to think of a data structure for S, where we can store this S to perform all this operation in a faster way. So, heap is a solution for that. Okay. So, heap is a implementation of the priority queue. That means heap is basically a data structure which will to store this, to implement this S, to store this S. So, what is heap? So, basically heap is an array which can be viewed as a binary tree. So, it is an array, just an array of say 1 to n. This is a array. We have so this is a array. We have given a array. So, now the question is, how a array can be viewed as a binary tree. So, this is the way we view a array as a binary tree. So, root is the first element, whatever element A1. So, this is basically A1. So, root is the first element A1. So, whatever the value over there will be the root. So, that is our A1. And then the next element will be the left child will be A2 and right child will be A3, and then this way we continue. So, then A4, A5, A6, A7. So, these are the indices. So, 1, 2, 3, 4, 5, 6, 7, like this we continue until the end of the array. So, this is the way we view the array as a tree, binary tree. Okay. And this tree is almost balanced tree, because height is n log n, because this way if it is, for example, if we have a given array this 6, 3, 7, 9, if this is the array, now how we can view a tree? We have to draw that this is A1, so root, so which is 6, so 6 is the root. Then the left element is 2, 3, I mean this is A2, A2 is 3, A3 is 7, so this way we continue. Then 4, A4 is 9, then A5 is 4, A6 is 5, like this we continue until end of the array. So, height is, if it is if the n is 2 to the power n, then it will be a complete tree. So, then height is, so it is a complete binary tree. So, height is always order of n log, order of log n, because the way we are designing the tree. Okay. So, this is the way how we can view a array, given array as a tree. So, just a visualization. So, that means this is the root. So, who are the child of this element? Child is 2 and 3. So, child of this element is 2 and 3. Now, if you take a ith element, say 3, 3I is equal to 3. Now, who are the child? 6 and 7. That means 2I and 2I plus 1. So, if you take a ith element or ith index element of this, then who are the child? Child will be here. So, this is 2I, say 2I is the left child, and the next element is say 2I plus 1. So, this is 2I plus 1. So, this is, if this is I, AI, this is the ith element of the array, we have a then the child are basically here. This is left child is 2I, the A2I, whatever the value over there, and this is A2I plus 1. So, this is the way we view this array as a tree. This is just a visualization. So, this is, we are not, so for implemented tree, if we have to say, for example, if we need to implement a tree in C. So, what we need to have? We need to have pointer for that. We need to get this left child, so left pointer, right pointer, or maybe some parent pointer also. So, but here we do not need to have a pointer, because if we know a I, we know where is the child. So, 2I and 2I plus 1 is the child of this AI. So, this array is sufficient. I mean, we do not need to have a pointer of for the implementation. So, this is the beauty of heap. So, heap is a array which is visualized as a tree by this way. So, every node, the root is the first element A1, and then followed by this way A2, A3, A4, A5, like this. We continue until the end of the array. So, this is our this data structure is called heap. Okay. Now, we will have two definition of one is max heap. So, max heap means the every node must be greater than from its child. So, we know if a node is ith node, so we have this AI, we have some portion of the tree in the above. So, this is true for all I. So, this is The childs are basically a2i and a2i plus 1. a2i and a2i plus 1. These are the child. So, whatever value. So, for max-heap we say a heap is a max-heap or max-heap array if for every node is greater than from its child, if this is true for all I. So, if starting from the root to the leaf, okay, leaf is there is no child. So, leaf we do not need to bother, but above that if we need to check this property, like if every node is greater than from its child. So, ai should be greater than a2i and sorry this is 2i. So, ai should be greater than this is not 2i plus 1, this is a2i. So, ai must be greater than a2i. So, this value if this is say 8. So, this should be greater than maximum of these two. So, this could be 3, this could be 5. So, what is the maximum? Maximum is 5. So, 8 is greater than 5. So, this is a this is true for at this level. I mean this should be true for all I, not a single I. So, this should be true for all I from 1 to n. We do not need n because we have the leaps also, but anyway this should be true for all I. Then we say this heap is a max heap. So, if every node is greater than from its child, then we say the heap is a max heap. Similarly, we can define the mean heap. If every node is less than from its child, then we call this is a mean heap. So, again sorry, okay, so this is a mean heap property. So, this should be ai should be less than a2i and ai must be less than a2i plus 1. So, that means ai must be less than minimum of this child values, key value. So, that is the mean heap property. Mean heap, we say that heap is a mean heap. So, in this lecture we will concentrate on the max heap and we will see how this priority queue can be implemented using this data structure. Okay. So, just to recap, what we have a how we can view a array as a tree, heap as a tree. So, it is a array where suppose this is the given array. So, where root is the first element, that is a1, a1 is the root, this is a1 which is 16 and then followed by all the elements. So, this is a2, a3, a4, a5 like this. So, the formula is for ith node the child is 2i, 2i plus 1, left child is at 2i for ith node and right child is at 2i plus 1. So, if we choose say I is equal to 4, then where is the child? For 4 2i is 8. So, this is the left child. So, for a4 this is the fourth a4. So, left child is a8 which is 2 and the right child is, so for 4 2i plus 1 is 9. So, this is 9. So, this is 4. So, this is the way we view this array as a tree and this is the formula for that. For left child we have we are at 2i and right child we are at 2i plus 1. So, this is the way we view and the parent is at I plus 1. So, this must be a lower ceiling. I mean this is integral part of it. It may not be a integer. So, this must be a integral part of it. So, suppose for example for 6, who is the parent for 6? So, 6 a6. So, it is a6. So, this is a6. This is 6. So, who is the parent for this? So, parent of a6 is basically I by 2, I is 6. So, 3. So, 3 is, so this is the parent of this. Now, similarly for 5 who is the parent? So, I by 2 is it is 2.5, but integral part is 2. So, this is the this is 2. So, this is the parent. So, this by this formula we can, and this tree height is log n because this is a nearly complete binary tree. It will be complete if we have more element, like if we have a number of element is 2 to the power n, then we have a complete string. So this is our heap, which is a array basically, and we are viewing this array as a tree. Now we want to have a max heap. What is the advantage of having max heap? Because once you have a max heap, okay, question is this heap is a max heap? This heap. So just look at the tree which is we are viewing. Look at the tree. Here, is this a max heap? This is okay. This is okay. 16 is greater than this child. 14 is greater than from his child. 8 is greater than from his child. 7 is greater than from his child. 10 is greater than from his child. Yes, this is the max heap. And if it is a max heap, you see the maximum lies in the root. That is always true. So that's why we are looking for max heap. So maximum lies in the root. So that's the reason we are looking for max heap. So now not every heap is a max heap. This in this exam we took this example to show this is a max heap, but not every heap is a max heap. If we change this is to be say some other number, say 12, and if we put 16 over here. So for example, so if we change this value, if we put this to be, sorry, let me, okay, so suppose this is the instead of 16, 7 is here, and this 7 we have 16. For this array, suppose our given array is this 7, 14, 10, 8, 16, 9, 3, 2, 4, 1. So in that case, the tree will be like this. So the root is 7, the first element, and then the left child, right child, then this way we draw the tree. I mean we visualize the tree. And so this is not a max heap, because you can see it is violation over here, because 16 is not greater than from his child, child is 1. Even we have a violation over here. So this value is, this node value is 7, this is a root, and say this is not greater than from his child. So this is not a max heap array. So it's not that every given array, every heap is a max heap. But if we have if we can make it max heap, then advantage is that we get the maximum from the root. So we get the maximum from A1 if it is a max heap. I mean after making it max heap. So that is the thing we are going to do. Given any unordered array, I mean given any array or any heap, we want to make it a max heap. So that is, if we can do that, we can get the max, and then we can do the remaining operations. So those are the heap operation we will discuss now. So so the heap operation we will discuss is first is max heapify. So max heapify, we correct a violation of a heap property in a subtree as it roots. So we want to correct a violation at some level I. So we have given a tree, we have given a tree. So this is a tree say. This is the array, I mean max heap array. Now we have some tree over here, and we have some ith element, and we have this sub array, left subtree, right subtree. So this is the sub array rooted here, this is the right sub array rooted here. Now we want to call max heapify at some index. Suppose we want to call max heapify at ai. So for that we have an assumption. Assumption is that this left sub array should be max heapify. So if we consider the tree rooted at this left sub array, and if we consider a tree rooted at right sub array, both are max heapify. So both are okay. So only thing we may have a violation here. So max heapify, this code, this max heapify can handle only one violation of the heap property, max heap property. So it will be called in some index. So, and the assumption is when you call maxipify on the index I, then we have to ensure that this subtree rooted at this left subarray, left child is maxipify, and this subtree rooted at the right child is also maxipify. Then only we can call the maxipify at ith level. So, that is the assumption we must have for calling the maxipify. So, we call maxipify at an index. Okay. So, then after getting maxipify code, we will discuss this. We will discuss another code which is build maxip, how we can use this maxipify to build maxip. So, that means given any unordered array, we can make a maxip array. That is our goal. Given any unordered array, we want to make a maxip array. So, that we will do using this by this function build maxip. So, we will discuss this in detail. So, let us first discuss the maxipify subroutine. So, maxipify is basically, as I said, we assume that everything is fine over here. So, this is the ith node and we want to call the maxipify in this level. So, we are thinking that the heap maxip property is violating here. So, for that we have to assume, we have to ensure that this part is okay. So, that means we have to ensure that the tree rooted at the left child are already maxipify and the tree rooted at the right child are already maxip. I mean not maxipify, already maxip. So, this part is okay and this part is also okay, then only we can call maxipify here. So, this can handle, maxipify can handle only one violation, and the idea is it will keep on go down. So, we compare these two value, whichever is the maximum, we swap with this. So, this will come down again. So, slowly we will discuss this code by an example. So, if the element violates the maxipify property, we correct by going down, taking down this to the tree and we keep on calling them. We will take an example to illustrate this. Suppose this is a given array. So, here we have array 16, then 4, 10, this is just an array. We are viewing this array as a tree. So, this is an array and we know where is the child and where is the parents, and this is the root A1. So, 16, 4, 10, 14, 7, 9, 3, 2, 8, 1, that is the array. Okay. Now, this is a heap, we are viewing this as a tree, this is our visualization, and this is not a maxip because you see here it is a violation over here, because this element is 4 and which is not greater than from its child. So, this is not a maxip. So, here is a violation. So, at this level. So, at this level we have a violation. So, that is basically I is equal to 2. So, now we want to call maxipify A2, I is equal to 2, but before that we have to check that assumption. What is the assumption? Because maxipify can handle only one violation. So, you have to check that assumption whether everything is fine in the tree rooted at the left child. So, this part is maxipify. If you see here, this is 14 and these two are less than 14 and this is the leaf node. So, we do not have to consider that. So, this is already maxipify, this is leaf node. So, this part is okay, and also this is the tree rooted and the right child. So, this part is also okay. So, we call the maxipify at this level at 2, I is equal to 2. So, when you call it, then we can consider the heap size is 10 because there are 10 elements over here. Now what is the code for doing this? We compare the child. Among these two are child of this. Among these, whichever is the maximum, we swap with this. So, 14 is the maximum. So, we swap 14 and 4. So, we swap 14 and 4. 14 will go here and 4 will come here. So, now this was maxipify, but we have the new member is joined in that subtree in the root. So, that may again violate the heap property, maxip property. So, again we have to call maxipify at this level, which index is swapping with the that particular I. So, then again we call the maxipify at this level. So, we call the maxipify on this, that index is 4. So, we again call the maxipify on A4, and then it will compare. So, it will check the child of it. So, child is 8 is maximum, which is this is not greater than this. So, we have to again swap with the max value. Max value is 8. So, we swap with 4 and 8. So, we swap with 4 and 8, and then again we may call. So, this is the new index where we need to call the maxipify, but this is a leaf. So, we do that will be the same thing. So, no more call. So, intuitively what is the runtime for doing this? If there are n elements over here, the runtime is log n if we start with this, because it has to go from root to that point to the leaf, basically height of that node. So, if the height is, because this is a binary balance, this is a balanced tree. So, this height is log n, because this is a nearly complete binary tree. So, that is why the time complexity is log n. Why the question mark? Because it is not always we need log n. Log n we need for the root if we call the maxipify at this level. But if we call the maxipify in the lower level, it will be the order of the height of that node from the bottom. So, that is the time complexity for that. So, now we are going to use this maxipify subroutine to in the build maxip code. So, build maxip code will give us take a input as a unordered array, any array, given array, and it will make a maxip array. Okay, so that we are going to learn now. So, this is the pseudo code for maxipify, whatever we have done in the illustration, this thing we are doing here, this is the pseudo code, you can just go through it. Now, come to the build maxip, which is the which takes a array of any unordered array, and it will convert into a maxip array. So, that is the idea. So, how we can do that? This is the very simple code, just 2-line code. Okay. So, this is the code for build maxip. We take the input as an array, A array. So, A array is an input, output is A array, but it will be a maxip array. Okay. So, this is the code, 2-line code. So, we have a for loop for I is equal to n by 2 down to 1. We call the maxipify. We know the maxipify function, right? So, we call the maxipify at I, at the level I. That is all. So, this is the code for build maxip. Very simple code, just a 2-line code. So, now the question is, there are few issues are there, why it is working and why it is n by 2 down to 1, why not from n down to 1. So, that answer we have to do. Why to start with at n by 2? Because see, suppose this is our array, this is our corresponding tree we are viewing. So, what are the nodes basically after n by 2 plus 1 to n? So, n by 2 plus 1 to n means these nodes. These are the nodes which are basically the leaves. So, leaves is already maxipify. Leaves means there is no child. So, we do not need to bother about them. So, we can just leave as it is. So, leaves are already maxipify, leaves are already maxip. So, we do not need to call maxipify on that. Okay. So, that is why we start from n by 2 plus 1, because why these are all leaves? Because if this is not a leaf, suppose we take any index after n by 2 plus 1 to n, if we assume this is that index is not a leaf, then where will be the child? Child will be at 2i plus 1. So, if it is greater than n by 2, then 2i will be more than n, but our array is ending with n. So, array there are n elements. So, these are obviously this n by 2 plus 1 to n, these are basically the leaves which has no child. So, they are already maxip. If we consider the tree rooted at that node, so they are already, so no need to call the maxipify for that. We only call the maxipify when it has a child, and that is starting with n by 2th node. This is the first node, I mean who has a child, that is n by 2th node. So, that is why we call the maxipify at n by 2 down to 1. And when you call it, if you see when you call maxipify on this first, this node, then it is just let me bring the laser. When you call maxipify on this, so it is having that assumption because it has a child which is leaf, which is maxipify. So, we fix that, I mean we compare these two, if it is greater than we bring it here, yeah. So, if it is less than we bring it here. So, similarly we will keep on doing this, and we are going like this, fixing like this, so that we must follow the assumption that left child the tree rooted at left child, when we call the maxipify at some node, tree rooted at left child are maxip and tree rooted at right child are also maxip, then only we can call the maxipify at that node, and that will preserve if we go like this. Okay. So, this is the code. So, now so we have to discuss the time complexity for this code. So, what is the time? So, before that we can just take a quick example on this before come to the time complexity, how it is working. So, suppose this is a given array, given unordered array input, we need to make a maxive array. So, these are our number A1, this is our A1, A2, A3, these are our indexing. Okay. Now, we call the maxipify starting from n by 2. So, there are 10 numbers, n is equal to 10, so n by 2 is 5. So, this is the first node which have a child. So, we call maxipify on this node. So, this is greater than, there is no change. So, then we call the maxipify on this node, but this is less than these two value, then when we call when we call the maxipify a comma 4, this code, then it will swap the maximum of these two, 14 will come here and 2 will go there. Again we can call maxipify, but this is already a leaf node, so that is already maxipify, you stop. Then we call maxipify here, this is less than this is not a maxipify, so we exchange this and this. So, it will swap with 3 and 10. So, A3 and A7 will be swap. So, that is what we did over here. Now, again we call maxipify here. So, this is this way we need to come back. So, we call maxipify here. So, it was 1. It was 1. So, we take the maximum of these two, we swap with this. So, 16 will go there and 1 will come here. So, we call maxipify on 2. Okay. So, now here we call maxipify on 2, then it will swap this, and again on that maxipify call we need to again call maxipify on this node, but this node is already maxipify, we no need to do. 1 will come here. So, we have to call maxipify on this, and this will swap with 7. So, again it will be, so that will be taken care of by that maxipify call of the this node. Okay. So, this way we continue, and finally we have a maxive array. So, again we call this on the root, and then finally we have a maxive array. So, this is a maxive array. So, now let us go back to the time complexity of this build maxive. So, how much time we are spending for doing this build maxive? So, to get the time complexity, let us come back here. Okay. So, we are calling this order of n times, right, n by 2 down to 1, and so intuitively it is n log n, because if maxipify will take log n, so we are calling n times, so n log n. But will it take log n for all the nodes for maxipify? No, log n will take only for this node, height of the tree. But if we call maxipify on this node, then it will be just come one level down. So, it may be one call of maxipify, then it will come down, then this is leaf, no more call. If we call maxipify on this, which is just 2 level from the lower from the bottom, then from the leaf, then that is just 2 call maximum. So, one call here, it will come here, under that call again we have to call maxipify at this level and then done. So, 2 call. So, the number of so the log n is not the maxipify time complexity for all the I, it will depend on where is the I. So, it is depending on the height of this I mean where we are calling the maxipify from the leaf node. If height is if it is root, then it is log n. So, that analysis we are going to do in more details. So, for doing that analysis, we need to know how many nodes are there just from one level above from the roots, above from the leaf. So, that is n by 4, and how many elements are there? They are 2 level above from the leaf, that is n by 8, and so on. So, basically it is basically this. So, for this n by 4 which are 1 level above from the leaf, for them we are doing constant work, just a one call of maxipify and maxipify taking constant time. So, it is theta of 1, and those who are just 2 level above from the leaf, for them we may need to call twice of maxipify. We first compare, I first call and then again come down and again maybe one more call. So, that is 2 call. So, 2C. So, 3 level above 3C. So, this is the sort of more correct time complexity for build maxi. So, if you simplify this, if we put n by 4 equal to 2 to the power k, so it will be this time complexity will be this the expression, and this sum is bounded by a constant. So, this is basically 2 to the power k, which is basically bounded. So, it is basically order of n. So, maxipify is a order of n algorithm. So, that is why we can use it for doing many things like build maxif, build maxif we already did, like extract the max, and then the especially heap sort. We will see how we can make use of this to have a sorting algorithm, and that is heap sort. So, this is the build maxif which is taking order of n time, not order of n log n time. This is the better time better bound. So, this is the order of n time algorithm. Okay, so this will give us a sorting algorithm which is basically heap sort. So, that we will discuss now. Okay, so let us now start the heap sort. So, it is a sorting algorithm. So, what is the input? Input is a given array of size n, we need to sort it. So, we have a unordered array or any array of size n, we need to sort it. So, that is the A array. So, what is the strategy for heap sort? We first make this array to be a maxif array. So, we call the build maxif on this array, and then it will become a maxif array. So, this is a maxif array. So, after calling the build maxif, this array will become this is a maxif array. This is a maxif. So, maxif means every element is greater than from its child. So, that means root contain the maximum, the largest value of the key. The root contain largest value of the key. So, that is why we want to do it. So, root contain largest value of the key. So, what we do? We know this is largest. So, we got the largest one. So, what we do? We swap this and this. We send this value to here and we bring the value over here to here. So, this is the largest one. So, we just discard this value from this heap size or from this array. So, this is in its if you have to sort it, then this largest will come here. So, this is in its correct position. So, we are sorting in increasing order, lowest to largest. So, this is in its correct position. We just swap these two, exchange these two. The idea I am telling, I will come to the detail of this. So, A1 and An. So, A1 is largest. So, if we view this tree, so this contains the largest element, and this has a value, which is this is largest one. This is not the minimum one. We do not know this value, but at least we know this root is the largest one after the build max heap. So, if it is max heap, then root is largest one. So, we swap these two. So, this value will come here and this value will go there, and we discard this. We discard this. That means, we reduce the heap size, array size by 1. So, then what do we do? Now, this is a new entry over here, whatever value was here. Now, for this, again for this sub array, do we need to call build max heap again? No, because we know that for this was max heap, because it was a max heap array total. So, this was okay and this part was also okay. Only we have changed the value over here. We have we have changed this value to a new value, replaced by a new value. So, that may violate the max heap. So, for that we need to call maxipify at this level, and when we call the maxipify, we know that assumption both the left subarray, tree rooted at left subarray and tree rooted at right subarray are okay. They are okay because that was the max heap. So, we may have the violation over here. So, for that we need to call maxipify, not the build max heap again. So, if you call build max heap again, then it will be again cost us order of n times. So, it will be log n order of n square algorithm. We do not need to do that. We just can call a maxipify again, maxipify on this level. So, that may again call depending on the value of these two, it swap with the largest one. Then on that call again it will call the maxipify, which one is swapping. Then again it may come down to the lip. So, that is the that under that call it will be again log n time. So, that is fine. So, that is in next level. So, again we on that sub, I mean on that heap, on that array. So, this will be the again if we call the maxipify, again this root will contain the maximum among this. Okay. So, that is the second maximum for the whole array. So, again we swap this and this way we will continue. So, let us write the code in details, the description. So, we first call the max heap, build max heap on the given array. Then the maximum element will be at the root A1, the first element. The tree we are viewing, it is just a array basically, we are viewing the tree. So, that is the maximum. So, then we swap the AN and A1 and AN. So, now the maximum will be at the end of the array. So, we can discard that that particular element. So, we discard that node N from the heap. So, basically we reduce the size of the array. So, we can have one more parameter on that size of the array, okay, reduce by 1, and then the new. So, when we exchange with earlier AN and A1, then the root, the new root may violate the max heap property. So, then we have to call the maxipify at the new root to fix it. And there again I am repeating, there we have following the assumption that the left subarray, I mean the tree rooted at the left child is okay because it was okay, and tree rooted at the right child was okay. So, we can call maxipify at that level at the root with the modified array, I mean size is reduced by 1. Then it will again become the maxip array after calling the maxipify. Then we again we get the maximum, that is the maximum among this subarray, I mean that is reduced by 1. So, that is maximum. So, again we that n is now reduced to n minus 1. So, we can have a, if we want to write the pseudo code, it is very easy to write. You have to put n is the size of the array, or you can use size of the array. So, size is reduced to 1. So, we go to step 2. So, we get the maximum, again we swap with the AN, the new n with A1, again we do the same thing until the array got empty. So, this is the code. So, every time we are doing the this thing. So, until we reach to a, so we will illustrate this over an example, then we will come to the time complexity of this code. Okay, so let us take this array. Suppose this is the input and we need to sort it. We want to use the heap sort to sort it. So we consider this array as a heap. So we can view this array as a binary tree, nearly complete binary tree. So we know how we can view this. We know the heap data structure. It is an basically an array which is viewed as a tree. So the first element is the root. So 16 is the root. Then followed by the left child, right child, then this way. So 1, A1, A2, A3, A4, A5. We know this. I mean the heap. This is heap. So this is our corresponding tree which we are viewing. Okay. Now we have to apply the build max heap on this to get a max heap array, because we don't know. I mean input could be anything. We have no control on the input. So we cannot assume that input is such that it is a max heap input. So we have to run the build max heap. So if you run the build max heap on this, we get this one. So this is a build. We took the example as a build max heap. Otherwise we have to run the build max heap on the given array, and anyway we don't know, we have to run it. So when we run it, we start with n by 2 down to 1, then we will get this same thing, because this is already a input is already a max heap array. Okay, so what we do? We just swap. So this is a max heap array. So before that we had to run the build max heap. So because input is any unordered array, we don't know whether this is max heap array or not. So we swap this A1 and AN. So this 16 will go there, 1 will come here. So we discard 16 from the, so 16 will come here, 1 will go there. So we can just write over here. So we just swap this to, okay. So this everything we are doing in array. See, this tree is just our visualization. We don't have pointer on all this, because everything is just the array and we are viewing this as a tree. So now 16, this will be 16 now, and this is 16 now, and this is 1. So we discard this. Now array size is reduced by 1. We forget this. Now this is our reduced array, and this is the corresponding tree of that. I mean the visualization. Now we know this 1 is a new entry over here in this position at the level 1, and here everything was okay, because this was a max heap after calling the build max heap. So this was okay, this was okay. We may have violation over here. So we have to call build max heap at this level. We have to call max heapify at this level. So we call max heapify at 1. So this is 14. So we have to this was 1. So we have to get this, swap this with the maximum element. Maximum is 14. So 2 and A2 and A1 will swap, and we have to call again. So this will be swapped. So 14 will go there, 1 will come here. Again we have to call build max heapify at this level. So when we call max heapify at this level, then 8 will be come here, because this is 1. Now 8 will come here, maximum between these two, and then again this will be again under that max heapify call. Again we have to call max heapify on this level. So this is 1. So again it will swap with the maximum 1. So 4 will come here, 1 will go there, and this is a, again we can call max heapify, but this is a leave node, there is no child, we stop. So this is the log n time, we can say, and then again it will become a max heap array. And then again this 14 is the next maximum. So we again swap with the last. This is the now situation. So again we swap with 14, and the last element is again 1. So we swap with these two. So 14 will come here, 1 will go there. We discard this, this A9 we discard, so array size is reduced by 1, so now the array size is 8, and then again we will do the same thing. We will again, so 1 will go there, again we call the maxipify at this level, so we will continue like this. We will call the maxipify at this level and it will become like this. After calling the maxipify, it will again come down. So that's why this call is order of log n. So that will be used in time complexity. So this is the next maximum 10. We swap this. So this way we continue. Okay. Okay. So now let us consider the. So this will continue until the we have done for all, until this effective size is became the array reduced array sizes became 1. So now let us talk about the heap sort time complexity. So heap sort time complexity, to let us just go back to the code. What we did, we did not write this pseudo code. This is sort of English description, but you can easily write the pseudo code on this. Okay, so how much time we are spending here for build max heap? This is order of n. We know this build max heap is order of n time algorithm, and just a one call. So we are just calling build max heap, and then rest. We find the maximum at A1. These all are, we are swapping A1 and An. So these all are basically, we discard this, all are theta of 1 time. And here we have again maxipify call. So this is basically, if the array size is n, this is log n, because it has to come down to the root to the lib node, and then we have a loop here, go to step 2 until the array size become 1. So this is the this is a loop of size n. So this thing, this is so from here to here we have a order of n log n algorithm, because for maxipify call, if the size is order of, until the size is or array size is order of n, then you have to worst case we have to come root to the leaf. So it is of log n. So there are so maybe for few, when the array size will be reduced to say constant, then we have a constant effort, but as long as it is a order of n, up say n then n minus 1, say n by 2, then also we have a order of n size array, then we have a, in the worst case we have to go from the root to the leaf. So that is the cost for calling the maxipify. So that's why it is, this loop is order of n log n, this up to this, and we have a order of n log n plus log n plus order of n. So that's why it is order of n log n algorithm. So this is basically order of n log n algorithm. So this is another sorting algorithm we have learned, heap sort, which is also order of n log n. So, but also we can think about whether it is in place or not. Yes, it is in place, because everything is doing in the given array. So we are just calling the maxipify on that array. So that array is became maxip array. So everything we are doing in that giving input array. So this is a in place sorting algorithm, and this is the time complexity for the any case, I mean worst case, best case, average case, because we don't care about the input pattern. We just have a input sorry, excuse me, we just have a input and we just apply the build max heap, and then we are doing the remaining things. So this is a in place sorting algorithm with time complexity order of n log n. Okay, so now let us conclude this lecture. So in this lecture we have started with the problem which is called priority queue problem. We have given a set S, dynamic set, where we are storing the key value of some records, and then we want to have some query, like we want to get the maximum, that is the priority queue. Priority, I mean who is the maximum, we can give the maximum priority or minimum this mean heap, we can give the minimum priority. So max heap is the maximum priority. So that is the priority queue. So heap we have introduced. Heap is basically a array which can be viewed as a tree, binary tree, and heap is a implementation of this priority queue, that for the dynamic set S we use this heap data structure, which is basically an array. We are viewing this as a key, as a tree, binary tree, and we do not need pointer to implement that, because we just view the trees we are viewing, we know where is the position of the sorry, left child and right child. And then we have discussed some heap max heap operation, max cpify, build max heap, and using that we can have this get the max of that element in that set, which is the root, and we can extract that. Extract means we get the max and delete from it. If we want to delete, we can just swap with the last element, and then we can call again max cpify on that, and then we get it. So it is basically order of log n, I mean log n time algorithm. If we have given a max heap array, we just get the maximum, I mean to extract, then we can swap it with the last one, and then we can still get the max heap array. And then decrease key, that means we can go to the any position of that array and we can change the value. And if we change the value to, again we have to call max cpify on that value, that index, and that will be log n time. And then finally we have discussed the sorting algorithm, heap sort. Thank you.